Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I have the pleasure of introducing Dan Reed, who's Microsoft's Corporate Vice President for Technology and Strategy and Policy in the Extreme Computing Group. I'm not going to read everything here on the slide here. It's a very long bio that Dan has. Prior to Microsoft, Dan worked as a professor at UNC Chapel Hill and was the director of RENCI. It was actually at RENCI where I first met Dan when he was co-chairing the 2007 eScience workshop with Tony Hay. As was mentioned yesterday, I think, by Dave Patterson, Dan served as a member of the President's Council of Advisors on Science and Technology and was the lead author on the report for Computational Science, Ensuring America's Competitiveness, and also served 2 terms as chair of the CRA, Computing Research Association, where he had numerous responsibilities. Also, previously the director of the National Center for Supercomputing Applications and was a principal investigator and chief architect for the NSF TeraGrid. Dan also served as Department Chair of Computer Science at the University of Illinois, and when I was emailing Dan while he was in Singapore this week about what I might say, I was wondering how far back to go, and I discovered I could go back 14 years. Because we have here at this conference one of his former students who was in his PhD program. I'd like to briefly introduce Fabio to say a couple of words about Dan as a professor.
Dan doesn't know anything about that. He probably doesn't even remember me because I was taking the PhD with Professor Roy Campbell at the University of Illinois. And I remember that everybody knew that Dan was a great researcher, but then it was announced that he would give a class on performance analysis, and I was very interested on that topic, so I enrolled for the class. And it was the most difficult class I took in my life. I had to study like crazy, but I remember how we enjoyed the class, and all the students enjoyed the class. When we had a class, we woke up in the morning happier, waiting for that moment in which we'll be in the classroom with them and having the pleasure of feeling the new connections in our neurons in the brain while he was talking. So it was a very enlightening experience. And just after that, he became the head of the Department of Computer Science, and it was a big change in the department, in which the department got the funds to create a new building, and that changed very significantly the infrastructure that the department has. And just taking that class with Dan influenced my whole career after that, I think. When I advise my students and when I teach, everything that I learned in that one semester, I try to pass to my students. So he didn't know that. And I bet there are hundreds of other students like me that were influenced by him. So just wanted to say that.
So it's my pleasure to introduce our keynote speaker, Dan Reed.
So I do have to now tell a story about Fabio because I do remember. Any of you who've been to Illinois in the winter know that it gets cold there. And him being from Brazil, I met him walking into class one morning, and it was October. And the frost had just started to come and the chill. And he said, "It's really cold here. Is it going to get colder?" And I said, "I've got really bad news. It's going to get a lot colder." So thanks for the introduction. I want to spend some time talking about several issues around clouds, a bit of cloudy forecast, talking some about what I think are the technology trends that are driving the interest in clouds, some issues around what I think are the opportunities to think expansively about the future of computing, and some sea changes that have really happened because of technology changes. Some about client plus cloud experiences, an attempt at perhaps horizon expansion, and then some about and so in some sense that's a discussion about what I view as application research challenges. And then some about some of the infrastructure and system software issue challenges around clouds as well. So if we sort of look back over the last 50 or 60 years and think about what's happened in computing, I think the key lesson of modern digital computing has been increasingly democratization. We've moved from a world where computing was rare and expensive to one where it's common and inexpensive. And yet, in many cases, I think our psychology is still dominated by an implicit belief that computing is expensive and that we should optimize computing rather than optimizing the human experience. And so the notion of what 21st century computing might look like, I think, is really a story of increasingly natural interfaces, and I'll talk some about that, about the fact that intelligence is increasingly embedded in everyday objects, and some of the pressures and challenges that exist around ubiquitous network access and communication. So I just came back from Singapore and giving a keynote at the Dynamic Spectrum Conference where we were talking about many of the issues about worldwide spectrum allocations and the ability to do cognitive radio to provide additional wireless bandwidth for the vast array of interconnected devices, what it means to enable these sort of natural interfaces. And so I want to talk some about these things. But remember, in the psychology, it's easy to forget so many things that weren't true very long ago. The fact that email was rare, that spam was mostly stuff that you ate as opposed to things that you worried about in your inbox, that phishing was still largely something you did with a pole rather than attempting to steal identities, that Wi-Fi and cellular were rare, and that friends were mostly people you actually knew, as opposed to social network friends. And so how we think about these social changes has a big impact on how we embrace technology and the ways that we think about building the enabling components that will make these new things happen. And so I think part of our challenge as researchers, whether in application domains or in technological domains, is to think expansively about the art of the possible. And as I said, I think often our language and culture constrains many of those things. And so I want to challenge some of those opportunities and issues as we go along. So let's think about what's changed over the last few years. We've got powerful system-on-a-chip designs. That's really what's allowed us to build mobile devices of a wide variety of types. GPUs that provide graphics performance and near photorealistic experiences that were unknown even a handful of years ago. The huge amount of explosive data growth that's itself a consequence of CMOS technology. And that has had some profound social effects on science as well. The fact that we've moved from a world where data was largely rare and advantage often accrued to people who had unique instruments, to the broad availability of data and the social change that says you can do better science than me, not because you have better infrastructure, but because you ask better questions, because we all have access to the same data. And then a whole set of issues around, as I said, computing embedded in everyday objects, the issues that I just mentioned about wireless spectrum pressure, and then all of the opportunities that we've been here to talk about new software models of clients plus clouds and how those things interact. I wanted to hark back, though, as a prelude to these discussions, to some observations that Jim Gray made years ago, that, as I said, I believe the challenges we face in this decade and future decades are increasingly multidisciplinary. And regardless of the domain in which we work, it's important to think about how we build tools and infrastructure that allow people to bridge disciplines, because the problems often lie at the intersections of those disciplines. And the cultures, in fact, are often our biggest obstacle rather than the technology. Years ago, I gave an opening talk at a meeting that was looking at the future of of technology to support building structure design. And I was staying in a hotel, and the meeting was in a nearby building. I walked out of the meeting, the hotel, to walk to the meeting, and there were two streams of people coming out of the hotel. One of whom were dressed very solemnly and seriously, as if they were perhaps going to a state funeral. And another group of people coming out of the same building in t-shirts and tennis shoes and shorts looked as if they might be going to the beach. And I was somewhat surprised to see them both entering the same building, the building where I was going to give this opening talk. And when I entered the conference room where the meeting was, I realized, in fact, that what I had seen was the group of civil engineers and the group of computer scientists. And I made some observations about the importance of mixing of cultures, and I had showed up at least dressed somewhat like this in long pants with a jacket. And I said, I'm here as a bridge builder between communities. So as we think about these interdisciplinary issues and how technology enables them, as Jim Gray observed, they are systemic problems. And the computation really depends on this balance about the characteristics of computation, of storage, of networking, and of data access. And to hark back to my professorial days, when my students used to ask for copies of old exams to prepare, I always reminded them that the great thing about computing is that the questions don't change, but that the answers do. And so just because you've seen the old exam doesn't mean that the answers are the same, because the ratios of access times and costs are really what make some things possible and some things prohibitive. And as we think about this new generation of client plus cloud, think back, 40, 50 years, to the fact that you could have done really great distributed systems research in 1962. One would have had to commandeer the computing resources of multiple universities and perhaps negotiate with the telecom carriers to acquire some leased 56 kb lines for wide area communication. But there's nothing intellectually that would have prevented one from having done that. It was entirely technically possible. It may have been politically impossible or economically non-feasible, but it was intellectually possible. And yet very little of it happened because of those issues. And so those ratios actually do change what we think about. And so part of what I think our opportunity and our challenge is to look forward and say, which of the things that are true now will continue to be true, and which of the things that are false now will be feasible and possible in the future, and skate to the future rather than just the present. So in that spirit, let me cast a few scenarios to think about before I talk about applications and infrastructure. Excuse me. So imagine some possible futures. One where your car drives and navigates for you, and maybe even parks. And that's increasingly a feature of many vehicles. What does this rely on? It relies on embedded intelligence, sensors, broad knowledge about traffic flows, and the broad set of issues related to urban planning and urban congestion. Think about a sound system that only plays the music you love because it knows every song you've ever heard. Again, an understanding of social networks and sensors and interactions. Imagine a phone that only rings when you want it to, because it not only knows what you're doing, but it knows the context in which you're working, and maybe even knows your emotional state, that this may not be the best time for you to have this conversation with this person. All of your family memories are recorded automatically. It's entirely possible now for a few $100s, a few €100, you can record every word you'll speak in your lifetime. Your body calls an ambulance when you're ill by virtue of biologically powered implanted sensors. A little more far-fetched, but you can certainly see many of those things coming. And your DNA sample determines, and your lifestyle determines the quality of health care you receive, because you really do have personalized medicine that's tailored specifically to your genotype and its phenotype and the environmental context in which you live. And your office, well, it's smarter than you are and actually adjusts its behavior to your needs by understanding the context in which you operate. Now, I don't know if any of these things are going to happen, but I know that we're on the verge of making many versions of these things true, and other versions that may be perhaps less positive. And so as we think about this interaction between technology and possibility and applications, social domains, and policy, we're really on the vanguard of making a bright future possible with the right set of opportunities and constraints. But all of these are examples of something that I think is pretty simple. Successful technologies, regardless of the domain, become invisible. The hallmark of immature technologies is that one is painfully aware of their limitations and of their explicit use. All of the things that we take for granted allow us to do things that we would not otherwise be able to do. I mean, think about something as prosaic as the history of the automobile. In the early days, if you weren't to first order a mechanical engineer and a mechanic, you dare not drive one because repairs were common. Now most of us rarely look inside the vehicle other than to operate it. It's true in lots of domains. And so as we think about how to empower people, the one thing that I remind myself repeatedly as a technologist is that the fraction of us on the planet who care about technology as an end is to first order 0% of the population. Most people care about technology as a means. What will it let them do? How will it empower them to accomplish things they could not otherwise do? And so as we think about client plus cloud, I think that really is the key message. How do we use client plus cloud technology to empower people in some new ways? And so one of the things that goes with this is to think about interfaces. And so I'm going to rant just a little bit about what I think is our failure of imagination to exploit this transition from powerful but very expensive computing technology to even more powerful and inexpensive technology. To first order, the way we interact with computing has not changed in the professional lifetime of everyone in this room. Yes, we've gone from batch job submission, where you were lucky to get one run a day, maybe on a batch machine with punch cards or punch tape, to a whole lot of relatively powerful graphical interfaces. But to first order, all of computing remains stimulus response. Those of you who are sitting here looking at your email or whatever, unless you do something, your laptop just sits there. You literally have to poke it to make something happen. It's true of touch displays and all of the other new things that we've seen. They are passive devices, and they rely on us to drive the interaction. And so as we sort of think about this history, as we've moved from batch computing through command line interfaces to GUIs, what happened with the internet, and the things that we're excited about with client plus cloud, and we think about those futures, remember what I said a moment ago about what happens when we have large numbers of very powerful, inexpensive devices. How do we shift the dialogue and the imagination from I optimize my behavior to the constraints of the computing system to how do I design and use a plethora of devices to empower me? And that means a wide variety of things. But think about this transition even from enhanced GUIs, where we have speech and we have handwriting and we have single and multi-touch, to what it means to build truly natural interfaces, where I can interact with client plus cloud systems as naturally and intuitively as I can interact with you. I can talk to you, I can gesture, I can wave my hands, I can foam at the mouth, I can reach out and touch, and you understand what all of those things mean. To do that, that means, in effect, relying on hundreds, if not thousands, of wirelessly and wired connected devices that understand my local environment, understand your local environment, share information, and rely on all the back-end infrastructure in the cloud for context. But that's a psychological difference between computing being rare and computing being common, and saying, I can use thousands of devices on a routine basis just to make sure I'm not late for my next meeting. So let's talk about clients and clouds and experiences. And the reason I wanted to hammer on that point is because the language shapes behavior. Anytime you or I say computer, we immediately narrow our scope of discourse to a vanishingly small fraction of the things that computing can do. The fact that all of us, here's an after-dinner question to pose to your non-technical friends. Ask them how many computers they own. And the odds are is they'll give you an answer that's a small integer. Probably in the 0 to 6 range, perhaps. Point of fact, all of us own thousands of computers. They're embedded in almost everything we use every day. And so that nomenclature really does shape the discourse. And so this notion of fixed and portable and mobile devices and even specialty devices is true, but the notion of client plus cloud with intelligent objects that support healthcare, that support intelligent energy management, that support social interaction, that I think is one of the great untapped opportunities. And it's true not only in social and consumer domains, it's true in the way we think about doing science as well. Because ubiquitous sensors can transform the ways that we think about capturing and analyzing data for scientific discourse as well. So let me talk about a couple of examples. And let's start with healthcare in this context. So the challenge and the opportunity of personalized medicine, if you will, what we've learned from genotype sequencing and what we increasingly know about gene expression and our understanding of its manifestation of complex disease, the yin and yang is how do we extend that technology to individuals worldwide, but do so in a cost-effective way? The great temptation, because of many social constraints, is to apply technology for protection or as an indirect consequence to increase costs for medical care. And if we want to broaden that base, then we need to think about some new ways of leveraging it, how we provide day-to-day experiences. And so what I was talking at the outset about what does it mean to say, I want to create an environment where the quality of your health care is related not only to your genes and their expression, but to the context in which you live. And perhaps equally importantly, how do I shift the dialogue from you go to your physician as a supplicant to request help when you're ill, to you being an active participant in managing not your illness, but your health. And that means how do I make available to you large volumes of information in intuitive ways that you can understand that context. And so as we think about this world of interconnected medical devices, how do we deliver high quality care and do so to scale costs in some ways that are increasingly efficient? And so think about some of those issues. As we think about using sensors for low-cost data measurement and diagnosis, as we think about client plus cloud solutions that would allow us to analyze that data and map it to personal circumstances, how we think about personalized drug delivery and tailoring, and then the broad set of issues around public health. As we monitor information and protect privacy of individuals, how do we exploit that data in effective ways to manage public health situations as well? So, how do we do this? How do we think about this vast array of devices, most of which, as I said as before, have embedded computing intelligence in them? They have the ability to capture and analyze data. They have wireless connections. How do we fuse that data and support insight, not for the physician, but for the individual in ways that provide insight? That, I think, is our challenge and our opportunity. Another example, let's think about the future of intelligent energy management and what it means to build a truly smart grid for an energy ecosystem. Everything from how smart devices that capture insight from your home experience and relay appropriate versions of that to the utilities so that they can manage dynamic load. How do we think about intelligent vehicles for traffic routing for hybrid vehicles and energy management, whether hydrogen or electric or battery powered, all the combinations that go with that. And what does it mean to manage and support lifestyles in that context? So there are some interesting studies about the power of intelligent energy management in industrialized countries that say that, and here's the key issue to think about, the energy intensive lifestyle that all of us in this room are accustomed to, the other several billion people on the planet aspire to, and the interaction of that energy demand with global warming, environmental change, is real. And so the question of how do we continue to deliver higher quality lifestyles but manage the total energy consumption, not only in industrialized countries but in developing markets to make those things happen while responding to climate change, is a big issue. And so all of these issues about distributed sensors and monitoring, and not only the client side, but the issues of cloud data analysis come together. And I want to just give you a concrete example of something that, that Microsoft announced last week as an example. And this is not a marketing pitch, it's merely an illustration. So last week, Microsoft announced a collaboration with Ford on electric vehicles. And it relies on a combination of technology that Ford is developing together with energy monitoring technologies that Microsoft has under the rubric of Microsoft Home. And this particular example is looking at the following question. So Ford's about to start shipping relatively soon electric vehicles in the US. And the question is this. So imagine a world in which there are millions of people driving around in electric vehicles. What do people worry about? Well, consumer study after consumer study says the nightmare scenario everyone has with an electric vehicle is they run out of electrons, right? That is the consumer worry. So there's the whole issue of how do I make sure I can actually do route management in a way that I don't wind up on the other side of the city desperately looking for a place to recharge my vehicle. But beyond that, there's the issue of what happens when millions of people drive home at the end of the day and they plug their vehicles into the electrical grid. Right? This is a massive hammer hitting the energy system. And so the notion of how one manages information about your lifestyle, when you travel, what it knows about when you might need to do what, and how one can do broad scheduling of charging to manage and load level at the utility level from that distributed sensor information is a big part of the story. And it's a client plus cloud application, absolutely. A very distributed one with huge centralized components. And so the notion really in some sense is this. So there's the concept vehicle, but if you look inside, and these are just concepts, the dashboard not only gives you status of the energy reserves of your vehicle, but it helps you do route planning based on traffic, but also on the availability of charging stations. And your mobile device may well interact with your social calendar to do similar kinds of things. This is what I need to do to manage my lifestyle and to manage the utility environment so that one avoids peak load demands that typically result in much less efficient energy generation. And then finally, let's talk some about science before I talk about cloud infrastructure. And this is a slide that I stole from Tony Hay, full credit here.
I stole it from Jim Gray.
And there we go. And Tony says he stole it from Jim Gray. And the Fourth Paradigm book is a tribute to Jim. But think about what's happened. And it's another one of these switches from scarcity to plethora. The fact that, think about the history of science. We went from science being mostly magic, if you will, to experimental science, where there was a fairly rigorous process to understand and measure natural phenomena. The emergence of mathematics and all of the theoretical studies that we have. The allusions made in my introduction about the fact that all of us, or at least most of us in this room, have been involved for many years in computational science. the fact that computing has become sufficiently powerful that we can build models of natural phenomena, or phenomena where experiment simply is either cost prohibitive or safety prohibitive or time prohibitive. In principle, one can do experimental analyses of stellar evolution, but probably not in any practical way that we could ever imagine doing. But we've shifted to a world of really data-rich science by virtue of inexpensive sensors and our ability to store large volumes of data. And as I was saying before, this is a hugely social change as much as a technical one, because throughout most of the history of modern science, advantage has almost always accrued to those who had unique instruments. If I had a telescope with more resolving power than you, I could observe phenomena that you couldn't. I didn't have to be smarter than you. I just had data you couldn't get. With the rise of broad sky surveys in astronomy, and with the rise of inexpensive sequencing technology, and you can go on down the line, we really have moved to a world where data is actually quite common. If anything, we're drowning in data, and the challenge now is extracting insight from that data. But I think the social challenge and change is perhaps more profound, because as I said, it has shifted many domains from data is rare and expensive, and I spend a big chunk of my career creating unique infrastructure to create competitive advantage, to the one where everybody has access to the data, and the question is, can you ask better questions than I am? Because we all have access to the same data. But that democratization of providing technology to allow those questions to be asked is really our client plus cloud opportunity. So we all know this explosion, and it's really what's driven the growth of massive data centers. So I'll give you one other example, which many of you probably know. Think about the rapid rise in quality of machine language translation. Computer science has been working on machine language translation since the beginning of the modern digital computer era. And it's gotten incrementally better year after year after year as we've attempted to derive better grammars, better rules that map concepts and syntax from one language to another. But the real lesson, in some sense, of cloud-based machine language translation is the power of data. If I have hundreds of millions of examples of the same thing being said in multiple languages, statistics becomes your friend. And that is really fundamentally, I'm exaggerating, but fundamentally one of the things that has rapidly improved the quality of machine language translation. We have samples, we have corpus at a scale we have never had before. Right? And the fact that Microsoft Research, for example, was able to create a quite adequate translation of English to Haitian Creole in the space of 4 days after the Haiti earthquake, an example of that. Right? And there are lots of other examples. But scale really does make a difference in many contexts. And this is what I was really saying, that we've moved from a world where it's hypothesis-driven. I have an idea, let me go capture data and find out whether the data supports this hypothesis, to one that's really exploratory. What correlations can I glean from the plethora of data that I do have? And that means different sociology, it means different tools, it means different techniques. It also means that for complex problems, simplicity really matters. Because those problems that span disciplines, the simplicity of the tools fundamentally determines whether one can tackle the problem or not. And that's really the concept of the fourth paradigm, that as we think about multidisciplinary interactions, and think about those examples I gave, delivering personalized medicine in a developing environment is not just a technical challenge. In fact, arguably, that's the easiest part of the problem. It's the set of economic issues, it's the set of political issues, it's the public health, it's the planning issues, it's the education issues, it's the promulgation and distribution of the technology, it's managing the social expectations around the use of the data. All of those things intersect with the technology. And so in the spirit that successful technologies are invisible, how do you bring together people across a dozen disciplines to solve a complex problem? Tools have to be simple. There's a great story that Fred Brooks used to tell at UNC, which I'll repeat again here. He said, "My objective as a tool builder is to build tools so powerful that a full professor will want to use them, and so simple that they can." And that's a high bar indeed. And it's even more challenging when you bring the people together across disciplines, each of which have that perspective, and will often lack a common set of concepts to communicate and have different social norms for success across the disciplines. Simplicity really matters. And that's one of the reasons why I think these opportunities of client plus cloud to support these multidisciplinary collaborations are so important. That the ability to deliver simple tools really matters. And this is a slide I stole from my colleague Roger Barget that really gets at the notion of, as we think about computing infrastructure, how do we enfranchise versus disenfranchise? I spent almost all my life in high-performance computing, working across disciplinary boundaries with people in a wide variety of technical domains. And I've observed fundamentally two categories of people. There are the folks for whom any new technology they will embrace to advance science. These are the folks that I would describe as the Marines on the beach. We may die in the attempt, but we will happily embrace the technology and use it. Those are code words for physicists. There is the other category of people for whom they will continue to use a familiar technology that's easy to use, even if there is perhaps a more powerful technology that is difficult to use. Those are code words for biologists. And those are gross characterizations. They're people in both camps. But there are fundamentally different psychological expectations across disciplines for tools. And so one of the questions is, how do we provide the power of those amazing new technologies and the simplicity of familiarity? So put it in concrete terms. There are people who will happily write a parallel application to run on a cluster and use a message passing interface to do that. Right? This is the assembly language of parallel computing. People do that all the time. There's another class of people that if you gave them that infrastructure free and all the software, they would never use it. This is too painful for them. They would rather run a spreadsheet for a month to do that calculation than write the equivalent code and run on a parallel machine and get the answer in 10 minutes. Simplicity matters. So how do we get those two things together? Well, we get the power of one and the simplicity of the other. So I think our opportunity in this client plus cloud world is to create this illusion that the powerful desktop metaphors and tools scale arbitrarily into the cloud. That my data access looks just as powerful on my notebook or my mobile device as it does if I'm directly accessing the database, that the computing capability scales as well, that my domain-specific and general-purpose desktop tools have arbitrary power and scale and scope for data management and computation, but they have the simplicity that they do that I'm familiar with for doing small problems. Right? That's our opportunity, and there are a huge number of underlying technology issues about that, as well as the disciplinary issues. And that Excel example is real. I know people looking at the spread of epidemics that in fact do build epidemic models, and they run for weeks or months in Excel. Because that's a familiar metaphor, it's easy to use. Now I can see some of you shaking your head saying, oh geez, I can't believe they do that. Well, they do. And so it works for them. But the scale and scope of the problems they want to solve reach beyond what those desktops can do. And so there are many ways. You educate, but you also ask, how can you address the limitations of those tools and preserve the familiarity? Because the social milieu really does matter. And so a lot of what my team has been working on is engaging with the community about these things in collaboration with Tony, looking at how we can engage the worldwide research community to talk about how we empower people, how we enfranchise the disenfranchised with more powerful experiences but familiar tools. And so we struck a deal with the U.S. National Science Foundation. We're in the midst of other negotiations with other research agencies worldwide to make available Azure technology as well as an engagement team to work with people on these issues of simplicity and client plus cloud tools. Let me turn, with that sort of backdrop about applications, to talk in systems geek terms about cloud technologies for a little bit and what I think some of the research opportunities there are. But the fundamental takeaway of everything I've said up to this point is convergent invisibility. How do we bring together the complexity of these hugely distributed systems but still maintain simplicity and move from procedural programming to modeling and visualization? Because that's what people really want to do. Programming is a means to an end. It's not an end except for a small number of us in computer science. How do we move from discrete tasks to being able to support context and intent? What does people really want to do? How do we move from trial and error to some more systematic processes that as we bring together increasingly complex multidisciplinary models, we have some idea whatsoever that we're not engaged in just a random process. So I'll throw out one other sidebar observation. If you look at the complexity of scientific applications, even with individual domains, but certainly as you think about fusing them across multiple domains, what's the probability that a complex multidisciplinary science application with 100 million lines of code in it is actually correct? Not high. Couple that together with increasingly those models are run on machines that involve tens, hundreds of thousands of processors and a complex underlying software infrastructure that itself is problematic about being fully functionally correct. All I'm really saying is a computational science experiment at large scale is an experiment in the same way that any experiment is an exploration of a distribution of the truth. Right? So if you do an experiment and you measure something and someone tells you it's 2 with no error bars on it, you should be suspect. If someone runs a computation and says the answer is 2, you should be equally suspect for the same reasons. And so as we think about this, there are challenges at that scale about verifiability and consistency. There are issues about privacy and identity that go with accessing these things as well. So what we're really talking about is how do we build a ubiquitous infosphere that spans disciplines, that spans technologies, that provides the right information in the right context at the right time. And how do we do in ways that meet quality of service expectations? So to hark back to what I said before, this is really about how do we move from stimulus response mode to allowing multidisciplinary teams to ask and answer interesting questions and have the computing environment not just be an aid, but be a partner. You know, much like my assistant, whom I jokingly but quite seriously say makes me look better than I really am, that's really what you want your computing system to do, is to make you look better than you really are by being an active partner in the things that you want to do. And that really does speak to this world of sensors and clouds. And there are a wide variety of issues about how we fuse these things together to do that. So let me talk about cloud infrastructure for a little bit, since I've been talking about clients and experiences. There's a lot of hype. Lord, there's a lot of hype around clouds, right? If you've been writing a research proposal lately, how many of you have taken that salt shaker and just sprinkled cloud on your proposal? Yeah, there's one. There's another. It's the way we play the game, and we all know that. There is an enormous amount of hype around clouds. But there's some truth in the story as well, and there are some really interesting systems research challenges around scale as well. So one of the other things I'd leave you with is, in the spirit of the questions don't change but the answers do, is anytime you add an order of magnitude, some of the truisms break down. Some things that we held true no longer scale, and we have to rethink some things. And there's some issues in cloud environments around that. Environmental responsibility is one of them. Big cloud infrastructures, a single data center can consume 50 to 70 megawatts of power. And a lot of that is heat dissipation, which goes back to our climate issue. How do you provision 100,000 servers? I'll tell you a funny story about this. One of Microsoft's data centers in the state of Washington, I was touring it when it was being built. There was one person whose only job was cardboard recycling. So if you buy 100,000 servers and they come individually wrapped for your protection, then some things change. So the whole notion of what's the right size Lego block at this scale, it's not a pizza box server. It's a different size building block. And the whole issue of how do you bring those things online quickly is an issue. How do you deal with the huge social issues around failure? Because when an increasingly large fraction of the human knowledge base is both digital and contained in a modest number of these massive data centers, there are not only operational consequences for the operators if they fail, there are huge social consequences for the planet if they fail. And so those management issues are real. And then there are a bunch of software and services issues around performance, reliability, security, and reliability is on there twice because it matters a lot. So one of the things to think about is a computer center and a computer room and a data center are not the same thing. You know, if you put up the standard science fiction movie vision of a computer room, you know, it'll look something like this. And depending on the vintage, there will undoubtedly be some spinning tape drives in the picture someplace. I'm sure movie makers everywhere are unhappy about the demise of spinning tape drives. Even blinking lights have gone away. So it's these long line of boxes, mostly gray or black. This is what we all think it looks like. And it's got a raised floor, and there's air cooling that comes up, and it's cool to a point that polar bears would be happy inside. Right? This is the standard view. Well, in fact, it's a whole lot more stuff. It's massive physical plant. It's operations and control. It's huge amounts of UPS battery backup. It's diesel generators to provide battery backup. And it's massive amounts of cooling. So a conventional computer room like that, scaled up to be a data center, as I said, can consume 50 or 70 megawatts of power, can evaporate 4 million liters of water a day of near drinkable quality. And that has some interesting environmental implications as well. The lead time to deploy these things is often dominated by how many 2 megawatt diesel generators you can buy and deploy. It's dominated by the battery backup, it's dominated by the water, it's dominated by the physical plant costs. And one of the things that's important to remember is this, that if you look at the cost of one of these facilities, about half of it is the computing, and the other half is the other stuff. This stuff is getting more expensive. This stuff is getting cheaper. And if you look deeply at these, you'll see cooling, power. Most of the cost somehow is related to energy management. So here's another thing that is not true that we've been led to believe. I talked about the fact that computer rooms are cooled to polar bear consistency. Well, in point of fact, if you look at what's actually true, you can run computing hardware at temperatures that are just short of burn your hands if you touch them. I'm talking second-degree burns. And the failure rate is only marginally higher than if you keep them cool. The reason why this matters is so much of the cost of running a massive cloud data center goes into cooling. And if you can make cooling go away, not only do you use energy more efficiently, you don't throw heat out in the environment, you reduce the total cost of physical plant as well. Right? So there are huge incentives to try to optimize some things that we historically didn't worry about. Because if you're standing up a rack of servers in a closet, you don't really worry this much about it. You should, but we don't. So if you look at the history of data centers that Microsoft has built, Generation 1 is what I was describing, with the cardboard guy. It looks just like raised floors, and you build massive amounts of them. Generation 2 was an optimized version of that stuff, and I'll show you some more pictures and details in a moment. Generation 3 went to bigger sized Lego blocks. And the notion that the building block one uses to build a data center is a shipping container filled with computing hardware. Right? It has 3 umbilicals: power, cooling, network. You drive it in on a truck, you lift it off with a crane, you put it on the concrete, you plug in the 3 umbilicals, it's on. That's the API. Right? And that shipping container contains several thousand servers. And the data center consists of a concrete slab, a bunch of utility infrastructure, and a metal roof. And ideally, you cool those things as little as possible. In fact, ideally, you don't cool them at all. Right? So what's success? Success means that I just came back from Singapore. You can build a container that you can roll out and plug in Singapore with no umbilical for cooling. It's just power and networking. Right? Because everything else is wasted. You, in principle, don't need it. And then the last sort of generation is, what do you think about modularizing the physical infrastructure, the power and other things that go with this? So let me give you some scale. These are overhead views of the Generation 2, 3 data centers, and they look like industrial warehouses. Well, they are. They're just filled with computers, and they're about 10 to 12x the size, and it doesn't really matter which kind of football field you pick, whether it's American football or real football. It's order of magnitude the size of one of those, right? The ones that are filled with shipping containers, and this is one in Chicago, and these in round numbers cost anywhere from $500 million to $1 billion a piece. They're even bigger. They're almost 20x the size of a soccer field. And Microsoft and its competitors are building a worldwide network of these things with all of the infrastructure that goes with them. The vision I was talking about is this, that says, and this is an overhead view of that Chicago data center, and if it looks like a truck stop where lots of 18-wheel trucks are parked, there's a reason for that. These are the shipping containers. And they're double height with computing in the bottom and basically all the utility support above. But those are your Lego blocks. And the reason for wanting to modularize at this point is you can go to hardware vendors and say, I'm going to define the API at this interface, but I don't really care what you put inside the box, as long as you can meet the service level agreement for my expectations about performance and reliability. And if that means you can do it with trained monkeys, and as long as we don't have to pipe in banana juice to support them, we don't care, right? Just meet the reliability and performance SLA that goes with those. And so the time to market issues about being able to deploy this stuff rapidly with pre-assembled components for all of the physical plant issues are parts of the challenge. And so with that context, I want to very quickly show you a few of the research challenges on the system side. So energy efficiency really matters, but in principle, what people want to do is optimize the ability to deliver operations relative to TCO, to total cost of ownership. How do I deliver service at the lowest possible cost. And there are a whole bunch of issues there about how efficiently do my services run. There are microprocessor and systems issues, all these issues about energy efficiency, the things I was talking about packaging and cooling, about the market costs for utilities and infrastructure, and then all the economic issues around the cost of people and money and time to market. So just as I was talking about these complex, multidisciplinary application challenges around personalized healthcare, or around energy management, or around research, there are analogs of those problems here. Because the traditional siloed approach that we would take to think about, I'm a networking person, or I'm a microprocessor architect, or I'm a database person, or maybe I'm an operating system person, is not enough to solve these problems. It's the interplay of multidisciplinary technical teams to tackle these things. So I'll tell you, I learned more about sanitary sewer system design in the last 2 years at Microsoft than I ever did in 30 years in high-performance computing. And you might think, wow, what do those things have to do with one another? Well, I was talking about those data centers and the fact that the traditional ones are cooled with water. And the cooling systems in those things, the pipes have algicide in them, right, to keep algae from growing in the cooling pipes. Periodically, you have to flush those things, and you have to dump that someplace. Well, it goes into the sewer systems, right, under all the appropriate regulations and public service processes. Turns out that algicide is too clean to go into the sewer system. It actually kills the bacteria in the leach fields. It's a big issue, right? So you have to think about things like that. You want to optimize cooling efficiency? Learn something about sewer systems. So my point is this complexity, the interdependence, is actually quite real. And so one of the things that my team is doing in partnership with folks across Microsoft is looking at how we take a systemic approach to these designs, how we look at processors, at storage, at networks, at packaging, at software, and say how do we do global trade-offs to try to meet some of these efficiency relative to TCO objectives. And I just want to quickly show you and plant some food for thought. And don't let me ramble on too long. Why has virtualization been such a hot topic lately? One of the reasons is because a lot of the workloads we run don't need the performance of modern processors. The fact that I could virtualize 3 or 4 workloads on a processor and still meet some end-user expectations. And that's not true for all workloads, certainly not true for many technical computing workloads, but it's true for many, for business workloads for sure. It's because those processors are far faster than we actually need. So one of the things you could do is say, well, okay, we'll virtualize the heck out of them, and that's what we do now. The other is to say, what can we learn from the mobile and embedded space and use lower power processors that actually achieve much higher efficiency? So if you look at one of these versus even a laptop, and you ask, what's the efficiency in terms of ops per joule that's achieved in a mobile device versus even a laptop? This is much higher, right, in terms of energy efficiency architecturally relative to operation count. It was designed because that's a pretty serious constraint. You won't use your phone if the battery only lasts 10 minutes. There are lessons to be learned there about how we think about building next generation data center processors and balancing energy efficiency, complexity, in order, out of order execution for appropriate workloads. And so I plant that as an architectural seed as food for thought. Think about storage at scale. And remember what I said about the fact that orders of magnitude matter. If you use any of the consumer advertised supported mail systems, in Microsoft's case, Hotmail, think about how many accounts there are for those things worldwide. Think about how much data there is. Think about how often disks fail. In a big data center, you can lose hundreds of devices a day. Right? If the mean time to failure is 1,000,000 hours and you get 1,000,000 of something, do the math. Right? You lose something all the time. Disks are our last remaining mechanical component in computer systems. And there is some hope as we look beyond flash, and flash in many ways is a stopgap technology, to things like phase change memory and other possibilities where we could have the byte addressability of DRAM and the resilience of block addressable flash and the reliability even greater than disks to change some of the dynamics. Because the challenge with disks, besides reliability at scale, is they're increasingly write-only devices. Just think about the economics of what's happened with commodity disks. You could buy a terabyte disk drive for a pittance today. And yet, if you ask yourself, how long does it take to extract a terabyte from that drive, they're bandwidth limited. The technology is optimized for capacity, but not for bandwidth. In fact, in many cases, the disks that are deployed at scale in data centers are only used to 10 or 15% of capacity, because bandwidth is the constraint, not capacity. It's better to use more disks at lower capacity to get more aggregate bandwidth. There are challenges and opportunities there to think about those things. Networking. Think about the history of TCP/IP. Right? When it came into being, 56 KB was blazingly fast bandwidth. It was predicated on unreliable, unreliable, low bandwidth communication. The data centers that I just showed you pictures of have more computers in them than the entire internet did a handful of years ago. In a small box, relatively speaking, with quite reliable communications and fairly constrained speed-of-light delays. How do we rethink the whole issue of the hardware-software stack for networking at scale and drive the economics down where we can build large networks at low cost that are reliable? And then one other thing I will foam at the mouth a bit about is the speed of light. And it's not very fast, and I wish it were faster. Tony hasn't been able to help me with this problem, physicists are not. And so what this means in many cases is we're building data centers that are islands. They're connected by a small number of 10 gigabit lambdas. And everything I said about self-similarity and storage of disks applies at data centers at a much larger scale. There are hundreds of petabytes of data in them connected by relatively thin pipes. What does it mean to embrace truly high bandwidth wide area networking and say, I want to provision, pick a number, 100 terabits of bandwidth, right? It's technologically possible right now, but we don't do it. I talked about the packaging and cooling issues, that we don't have to cool for polar bears. There are other options. I talked some about reliability and resilience. One thing you might ask is, when hardware is cheap, why do I worry about making it reliable? Why don't I just buy more of it and over-provision to tolerate failures? Because it's getting cheaper and cheaper. And that's a different psychological model, because we generally try to think that our hardware is reliable. Well, at large scale, it's not, right? Statistics doesn't lie. And then there are all the issues around trust and privacy and security. And this is a complex set of technical issues as well as political, economic, and social issues. How we develop differentiated SLAs that allow us to deal with different expectations about privacy, reliability, performance for different kinds of workloads. There are some deep issues around that. And then a broad set of energy issues. How much you think about using renewables to power data centers. There's a whole interesting set of technical issues around what happens if the sun goes down and my data center doesn't have power anymore. Well, dynamic load distribution, load sharing, there are deep systems issues that go back to networking, software distribution, global consistency that come into play. And we're working on those issues as well. And as I said, there are these SLA issues. So let me leave you with this last thought. As we think about all of these complex multidisciplinary issues on the application side, on the physical infrastructure side. And they're sort of summarized this way. What bounding box do you draw around the problem? If you define it narrowly, then that will define the context in which you attack the problem. What kinds of workloads is one trying to provide? And perhaps equally importantly, or maybe even more importantly, the metrics of success you choose, reward or punish. Just like writing research proposals, if your academic institution rewards you on papers published and money brought in, well, we're all smart people. We'll go optimize for those two metrics. Those may or may not be optimizations for insight and knowledge creation, but these are the worlds in which we live. As I said, component failures are real at scale, and people and machines don't mix well. And we've historically mixed them. There's no reason why a lot of this infrastructure has to be human habitable, and these multidisciplinary solutions really matter. So there are systemic architecture issues writ large, is really my takeaway message. So we need to think about end-to-end perspective in some broad ways. The clients, the clouds, the applications, and the broad set of issues that go with creating experiences and holistic design and intelligent management, and in fact, all of the policy expectations that go with that. And I see Kent's getting nervous. I actually am done. So thank you very much for listening to me this morning.
We have a few minutes for questions.
Thank you very much for a very inspiring talk. I wanted to question one of the comments that you made on the general thrust of science early in the talk. You mentioned that there's a switch to from experimentation to observation of existing to analysis of existing data, and then you make the connection with a switch from hypothesis-based to analysis-based science, and I don't think the connection holds at all. I don't see the argument. I mean, of course, there are two kinds of research. There's deductive, where you start from what you have in your mind, and inductive, in which you look at the data. And it seems to me that the case for scientists working mostly in a deductive fashion was made very convincingly by Popper, by Kuhn, by Bachelard, and people like this, and I don't see at all how the availability of more data changes that. If anything, it should actually make initial hypotheses even more important, because if you have this huge amount of data and you just analyze it without any a priori scientific hypothesis, you are just going to find all kinds of bogus connections. So I don't follow you here.
It's a really good observation, Bertrand, and let me try to recast what I was saying. I completely agree with what you said. Two comments. Fourth paradigm does not mean the only paradigm. It's a complement to the other three. What I was really trying to say about the broad availability of data really is perhaps more operational in the following sense, that when the pain and cost of acquiring data to test a hypothesis is exorbitant, then you design the infrastructure to capture the data, driven explicitly in most cases by that hypothesis, to be able to test it. When there's broad availability of data before you even think about the problem, then you have some existing context. I mean, you always have had, but in a much broader, richer way than before. And it's possible to start asking questions with existing data, and in some sense to apply a broader range of statistical techniques than we once were able to. One of my astronomer friends used to joke that, who is a variable star observer, oh great, I found 3 of these, now I can do statistics on the problem, because I can compute a variance with 3. And we've sort of moved beyond that in the sense that there's broad availability of data and you can ask questions from it. And I think in that sense, it's democratizing in terms of availability of data and infrastructure. That's all I was really trying to say. I'm not quibbling with the epistemological issues about the nature of research. I completely agree with what you're saying there. Dave.
Hi, Dan. I guess as a former academic, you know that we're accused of not being very good at multidisciplinary research, and I think
I've been accused of that too.
Yeah, so that that's kind of your call, right? So now that you're not an academic anymore, what advice do you have for us to do that better?
So I think it's a good question. I wish there's an old story of Mark Twain in Life on the Mississippi when he was learning how to navigate the Mississippi River as a riverboat captain, and he was being grilled by his trainer, and he said, I was gratified to be able to answer, and I did. I said I didn't know. And that may be part of my answer to this question. I'm not sure I know. I think it goes back to the rewards issue, frankly, and the metrics at many levels. I think some of it is related to the way that we have structured our educational system. It's certainly related to the way our national and international funding mechanisms work. And what I would like us to try to do is change some of those things. I mean, and those are painful social processes to do. If you think about, I used to be on an advisory committee for a European university, a long-standing one, and I was talking to the rector at one point, and I said, if we were to awaken one of your predecessors from the Renaissance, I'm pretty sure they wouldn't have any trouble stepping right into management, because the structure really hasn't changed much in the last 600 years. And that comment is equally applicable to universities, mostly worldwide. And there's some good things about those eternal verities. There are some things that have stood the test of time. But I think this is one instance of a broader problem that is a consequence of technology evolution, that the rate of technology change in a huge set of social domains has outstripped the rate of ability of our social structures to adapt rapidly. And job skills being a concrete example, right? The notion that when you leave the university system, you have job skills for a lifetime was true of our parents' generation. It's not true of anymore. Perhaps the only sustainable skill you learn is how to educate yourself, and you hope that you'll be able to continue to apply that. But the notion that you have a concrete set of skills that extends is breaking down, and I think these multidisciplinary research issues are in that same context. So trying to get people to think and work in teams, I think, is a university issue. I would like to see our funding mechanisms, and I should say this issue is not unique to academics. I think it's true of corporations as well. It's an artifact of human social organizations, that reward metrics have to bring people together. And do I have any magic for that? No, but I think that is the killer issue, and it's an astute observation.
Okay, thank you very much.
Thank you.
We now have a